Well, hello and good morning to you, or good evening, whenever you're watching this. We're going to do a little bit of a review of some things that you probably have heard several times, but let's go through it. Maybe you'll pick up a few things that you're a little bit rusty on. So first of all, we're going to make sure we've got the pen rolling here in case I want to make some notes here. Make sure the pen's rolling. Let's go up here to the upper left. Yeah, looks like we're good. Make a little smiley face. Someone's looking down on us. Okay, so we're going to talk about exponents and how to graph them. And this is what they look like. And it looks as though we've got a little typo here. Right there. That should have parentheses. And so we'll make a note of that so I can fix that. Alright, slide number 3, and you've got 3 different functions there. You can see you've got the quadratic function, you've got the square root function, and you've got the reciprocal function. Slide 3. F of x. Okay, moving along. So those are some algebraic functions. Remember, if you can write as y equals and then everything else after that is x, you've got a function working for you. If you switch the roles and raise the number to a power that's got a variable in it, then you've got an exponential function. Things are a little bit different then, but not too hard. If you've had any trouble with it in the past, we're going to fix that. So this is what an exponential function looks like. And here we are. So f of x equals a to the x, or y equals a to the x. We're not going to use a 0 because that would be pretty silly, and 1 would be pretty silly as well. And in fact, we're going to use positive a's because very strange things happen if you try to use a negative number where that base is. So one example is because that a is just a constant. It's not a variable, even though it might look like it. So maybe 7 to the x power, or maybe 13 to 2x plus 5. Those are 2 good examples of exponential functions. Next, a few properties, and you could memorize these or not, that's up to you. Occasionally they become handy if you know them real fast, but it's not that terribly important. Almost anything to the 0 power is 1. As long as that power is 0, you get a 1. So for example, remember that e we talked about in an earlier time? 2.718, and so on. Euler's function. If we take e to the 0 power, you get 1. If you have a 7,258 to the 0 power, 1. No matter what it is, to the 0 power, it's 1. The second one, if you've got the same base, that's very important. If the bases are the same and you're multiplying, you just add the exponents, because this tells you how many a's you have here. This tells you how many a's you have here, and so when you multiply them together, you end up with the sum of those two. The x a's here and the y a's here, for example. Let's suppose we've got 2 to the 7th times 2 to the 11th. Since this means there's 7 2's, this means there are 11 2's. All told, you've got 18 2's as factors. Next, if instead of multiplying you're dividing, well, it would make sense that if when you multiply you add, then when you divide you subtract the exponents, because here this means you've got a certain number of a's and you're dividing by a certain number of a's. So some of those on the top will cancel, some of those on the bottom will cancel. How many are left? All you have to do is subtract. An example, 2 to the 6th over 2 to the 2nd. Remember, you've got, this means 2 times 2 times 2 times 2 times 2 times 2, and this means 2 times 2, so it takes care of one, it takes care of another one, so you end up with 4 of those 2's. Shortcut, just subtract 6 minus 2. Even if there were more on the bottom, if you had 7 to the 3rd power over 7 to the 9th power, just subtract those exponents, top minus bottom exponents, 7 to the minus 6th. And of course you could rewrite this as 1 over 7 to the 6th. If that number weren't quite so big, you actually might multiply it out. If it were a 2, for example, you might do that. Or if this is your final answer, you might multiply it out and see what it is. You might write it as a fraction, or you might write it as a decimal. It depends on the situation. Next one. This one, take note that this one and the last one, oops, not that one, this one and this one sometimes are confused. Here you got 2 different factors, and you have x of the a's here, y of the a's here, so you add them together. This is different. This means you have a to the x, and you're going to have y of those a to the x's. Well, that's a whole bunch of a to the x's. You don't want to have to add up all those x's. A shortcut is just take x times y, the inner exponent times the outer exponent, and that becomes your new exponent for your base a. Next one. This is sort of like the distributive property in a way. You've got a product inside parentheses, AB, and you're taking it to the x power. And all you have to do is split it up. Each one of them gets the exponent of x. So if you had 8 times 3, and that was squared. Another way of calculating that would be take 8 squared and multiply times 3 squared, and whatever your answer is. I am not going to try that in my head. And last of all, I think in this group, no it isn't, it's next to last. This former one, the preceding one, is very much like that one. If you've got a quotient inside the parentheses, then each one of these bases gets the exponent. A gets the exponent, and B gets the exponent. So if you have 5 over 17 to the 3rd, Another way of calculating it could be cubing the 5, cubing the 17, and keeping the fraction. And last of all, we've got negative exponents, and we've used this before actually, but that negative exponent actually reminds you that you're talking about the reciprocal of a to the x. Negative always reminded me that this was on the wrong side of the fraction bar. But you probably have your own way of remembering what to do with it. Next, some examples. Notice you've got the same base. And if you've got the same base, you can just add the exponents. Notice that if you had 5 squared and you add 7 to the third, you can't do that this way. You have to have the same base to be able to add the exponents, and if it's small enough, go ahead and multiply it out. Second, even if one of them is a negative exponent, you still can add them. Add them, and then express the result the way you're supposed to. Here's a power to a power. Don't mix that up with 3 to the second times 3 to the second. It's a power to a power. That's when you multiply the exponents, because this means you've got 3 squared times 3 squared times 3 squared. 3 times you've got 3 squared. So you just multiply the exponents, and since this is sort of small enough, you can multiply it out. You probably would use or express your answer as 729 instead of 3 to the 6th. How about graphs? The graphs aren't too bad either. There are a couple of points in particular you want to look out for. So here are 3 examples, and let's do a speed graph on these things. Let's see, got a graph coming up here. Just use that. So the first one is 2 to the x. Notice that this is a constant. You're taken to the x power. This is not 0, it's not 1, it's greater than 1, so we're in business. Now, how do you graph it? Well, one point you always know is if you put a 0 in for this x, you get a 1. Remember that? So 0, 1 is going to be one of those points. See where I'm graphing it down there? And if I put a 1 there, I'll end up with a 2. So 1, 2. I've got a pair of points already. Now, one of the things you'll get familiar with is, first of all of these have the point 0, 1. All of them, period. All the exponential functions in their basic form go through the point 0, 1. Even 3 to the x. The 3 doesn't change that. It still will go through 0, 1. And the basic look is like this. Once you've got a couple of points, and you're familiar with this, it goes sort of like that. And on the left-hand side, it approaches the x-axis. Remember, that's an asymptote. So the x-axis is an asymptote on the left. And it rises, excuse the expression, exponentially on the right. It rises quickly and without bound to the right. For the second one, we've got a base of 1/2. You can write it as 2 to the minus x if you want to. You still have the 0, 1. What does change, though, is if this is a negative exponent, what it's going to do is it's going to switch this like it went through the mirror. So on the right side, it'll be asymptotic to the x-axis, and on the left side, it'll go like that. It still goes through 0, 1, 0, 1. That's your buddy for exponential functions. That's the starting point. If it's got positive, if this a is greater than 1, it's going to look like this. If a is between 0 and 1, it's going to look like this. And as I said, this one, remember, still goes through 0, 1. Since this is greater than 1, we can rough this in. Well, this isn't very good, sorry. Something like this. And asymptotic to the x-axis in this direction. You can also do this by just graphing a bunch of points and recognizing what it's going to look like basically before you start. That's a big help. And you get a bunch of points and then smooth in the result. So for the first one, you get some points, pick some x's, fill in this table. For the second one, pick some x's, put in this table, and so on. And some good x's to pick. 0 is always a nice one because that makes things rather easy. Using a positive one is pretty easy usually, and negative one even. Once you get those 3 points, that sort of gives you an idea what it looks like. Add a couple more, and you're in business. So those are the 3. This is what you probably will think of when you think of exponential functions. You think of 2 to the x, that's going to give you an idea of what it looks like. And then there are adjustments you need to make if you see that it looks a little bit different from a simple 2 to the x or 3 to the x even. Notice those graphs look very similar, except that even after the 0, 1, which both of them have, because the 2, this one goes to 1, 2, this one goes to 1, 3. Just a slight change, but from a distance, it looks very similar. So the two of them, the first and the third, are increasing. The second one is decreasing, obviously. Because remember, increasing or decreasing, we're talking about what are the y values doing as you scan it from left to right. Here's some things you can keep. But it's not as important as just knowing how the graph goes. It is 1 to 1. You can switch the x and the y values and still have a function. And domain and range are as you see. Domain everything, range starts at 0, goes to infinity. Of course, you've got the 0, 1 for all of them, basically. Now, if you want to graph this one, what have you got? Okay, first of all, start with this. What does that look like? And this will be an adjustment off of the 3 to the minus x. So if you're going to graph that, excuse the drawing here, you know that that's going to go through 0, 1, this basic one, and because it's a negative exponent, it's going to go something like this, roughly. Now this minus 1 says every time you do this, before you get your y value, before you decide on the y value, you have to subtract 1 from it. So every one of these points on the basic one drops down 1. So 0, 1 is here, and it's going to approach -1, and the left-hand side will do something like that. So just grab a hold of this basic one. The -1 says pull it down 1 unit, and you got your graph. Get a table of values like that, that's an easy way to do it. But what I showed you is a good ballpark figure that you can get in your head. That way you know where you're headed, and when you create your table of values, if something doesn't look right, go back and recalculate. You probably had a calculator mistake or a mental mistake when you're calculating. From the limit. Excuse me. You want to get the limit. Remember, one of the properties is you can split these two. The limit of 3 to the minus x and the limit of 1. Of course, this isn't affected by what x is doing, so this is just a minus 1. The minus because of this, and the 1 because that's a constant. And the 3 to the minus x, rewrite as 1 over 3 to the x, and you got your answer. That gives you the horizontal asymptote, because this tells you what is this function doing when x gets bigger and bigger and bigger and bigger. It's getting close to -1. Look back here, you can take a look at this, and remember this is the dotted line here. It's getting closer and closer to -1. Back up to where we were. There we go. So that's the horizontal asymptote. And that's the final figure. And that's it for your introduction to exponential functions. Actually, it's probably just a review, I hope, because you would have seen this in algebra, algebra 2. You've seen it in a lot of different places. College algebra, pre-calculus if you took that. Anyway, that's it, folks. I'll see you in the next lecture. Bye-bye.